Hello, my name is Koyan Dimitrov and I'm studying at the American College of Sofia. A couple of years ago, I read about three American scientists who were able to create a tiny flying robot which they called the RoboBee. At first I wondered how this could be any useful. I mean, a robot of such size wouldn't be able to carry out any meaningful tasks. But then I realized that a swarm of such small robots could achieve much more than an individual robot, regardless of its size, ever could. I could think of many applications: artificial pollination, search and rescue, security, exploration of hard-to-reach areas, searching for mines after war, or even evaluating the radiation, chemical or biological hazard of an area. But all of this is hidden behind a tough challenge. How do we make robots communicate and cooperate with each other? This is the problem I set out to solve. I looked at how ants in nature perform foraging and how effective they are at it. And I tried to introduce that to microrobotics. But since I didn't have any physical robots, I instead created a computer simulation, which I will now demonstrate. Every robot represented by a black dot has a sort of virtual pheromone map it keeps in its memory. In a certain interval of time, the robot leaves a pheromone on its map. When two robots are within communication range of one another, they exchange their pheromone maps. The robots then use those pheromones to decide the direction in which they will move. Whenever a robot is deciding, it looks at a number of possible directions and assigns each a desirability rating. The rating is calculated based on the distance to each pheromone on the map and its strength. In essence, this means that robots try to stay away from the pheromones so that they do not repeatedly visit the same place. Further, each robot has a battery displayed above the black dots. When they are low on battery, they move to the center so that they can recharge and resume their task. This simulation can be controlled by multiple parameters. Firstly, robot count represents the number of robots simulated. Let's set this to 10 since simulating a high number of robots requires a lot of computational resources. Communication range is the maximum distance at which the robot can exchange pheromone maps. I'll set this to 100. Failure chance is what is the chance that a robot fails each second. Let's put it at 1%. Robot speed controls the movement speed of robots, while battery discharge rate determines how much battery a robot loses in a second. I'll put this to 15%, even though this value is extremely high. Considers future positions dictates the number of possible directions that a robot assigns desirability ratings to, as I already explained. Finally, pheromone decay rate controls how fast pheromones lose their strength. For example, leaving this parameter at 0 is best for one-time searches, say a lost person in the mountain perhaps, while a greater pheromone decay rate means that the more time that passes since a robot last visited that area, the more likely it is going to visit it again. This ensures somewhat equal distribution of the robots and allows revisiting areas while also reducing blind spots. Let's set this to 15%. If we now start the simulation, we will see how the robots disperse from the center but quickly return as their batteries discharge with the enormously high battery discharge rate. On the right, we have a number of checkboxes that determine which pheromone maps are shown. If I toggle Robot 1, we will only see the pheromones on the pheromone map of Robot 1. Now, as time passes, we will see that some of the robots disappear due to the failure chance. Of course, there are many possible improvements that could be made to the simulation. The main one is definitely performance, given that simulating more than 50 robots requires special computer hardware. While I already talked about the many applications of such a robotic swarm, this simulation too has practical uses. Given a unique situation, the simulation can be used to determine optimal parameters for later use in the real swarm. Overall, using ant colonial behavior in nature to coordinate artificial swarms proved successful. I can definitely see this system being put to good use and greatly contributing to the 17 Sustainable Development Goals of the United Nations.